In 1999, there was 250 million people on the internet. Today, that's 4.5 billion. I was going through my stuff and I found a poster of what the whole internet looked like in 1999. Here it is. As you can see, there's a bunch of blue grids. All those are networks. Other colors are government, others are commercial entities. Everyone thinks they know how the internet works, as it's a collection of networks. But what does that mean? Today's video, we're going to go over how all this stuff is interconnected and how data actually gets from your computer, through the provider, through the internet, and then finally to its destination. There's two main parts to the internet. There's their service provider part, and then there's the destination where it's trying to reach, whether it's your email, website. So the internet service provider's job is to get it to their edge. That's all they control. From your house, where you type something in, through the data path that they choose, out to the edge of where they control. That's what their main job is. Once it goes to there, it's really up to the internet to decide the path it takes and how it gets there. Every network out there has an autonomous system number. This is just a number that's assigned to you from a company called ARIN. That's the American Registry for Internet Numbers that controls all of North America's IP addresses and AS numbers and other network information. An AS number defines a whole network, like a whole ISP, such as like CenturyLink or Google or Microsoft. They all have one number that defines their whole network and all their boundaries. IP addresses are assigned in blocks to those AS numbers. Those IP address blocks are known as prefixes. So data through an ISP's network is a lot like driving a car. You have a destination and an origin. So they actually use a very similar algorithm called the Dijkstra algorithm, which defines where you start, where you end, and the path that it takes through it. So here I have a computer that hooks up to a router. And on the router, you have your local network, which stays local to here. And then you have an internet port that will go out to whatever kind of network you have. We have a lot of wireless connections, but we also have fiber. And this will go up to one of our towers. Once it hits the internet side, that's when our routers will decide where it goes. So when you hook this port up to an internet site, it's getting an IP address or an internet number from your internet service provider that then tells it its next destination. So everything that you look around really is, what is its next destination? So from your internal router, its next destination is one of the receivers up on some kind of tower somewhere around town. From that receiver, it has a destination of a router or switch such as like this. From the device up there, it's going to go into one of these cables. Once it hits there, it's going to go over your ISP's routing policy, whether it's a dynamic or a statically set one. But that doesn't give you the luxury of some sort of failover. Now, if you do have a problem of, say, this cable goes down and that's where all the traffic is going to, well, you got a problem. Your traffic's just going to stick here. But if you have some kind of dynamic routing policy, if I unplug one of these cables that is the exit point, it'll find a path that goes somewhere else. Such as when I design a network, I usually do it in a ring so that there's one point that it can go back that one way or one the other way. So if I pull this out, it'll just go on to the next hop. It might be longer, but it'll get to the place where you're asking to go to. So an ISP network has multiple paths out, and a lot of them will look like a web. So from that web that has multiple exits and entrance points, you want to assign costs or different metrics to which you want to be the quality of the link, the speed of the link, and you want it to be able to choose based upon what you hard set as the best path. Here's one algorithm that a lot of people use. It's called Dijkstra. All these are doing is taking data from your house to the core. So now we've exited the internal part of the network, and now we're going to the external part that actually talks to the cloud, such as other providers or carriers. And this will be your main router that has a lot of carriers plugged into it by fiber cables, usually. And then they will choose based upon a protocol called BGP which one it exits. So back in the day, you would get a private line from one company to another, and that would give you an interconnection point. Nowadays, everything goes through big carrier hotels. One of those is known as like One Wilshire in LA. All that building is there for is really for connection points between one network to another. You'll go there and you'll see and look up and you'll see huge cable bundles bigger than you could wrap your hands around that are just full of fiber cables that connect one carrier to another for one purpose or another. So here we have one of our core routers. So I have my AS number, and each one of these cables is connecting to another AS number out there. When they connect, that's called peering. So when I peer, I'm downloading the whole internet as they see it into my router. My router is going to download it for all these cables and basically make its topology of the way it sees the internet and what its fastest path out to one of the other destinations or whatever you're trying to reach would be. So when one router connects to another one, the things that are downloading are the IP address blocks for everything out there. Currently the internet's about 800,000 prefixes. Depending on which prefix is in its destination, it's going to hit your core router, and then your core router is going to send it out what it sees as the quickest autonomous system path. That autonomous system path is made up of the different networks it has to transit in order to get to its destination. So when a carrier hotel and you get that fiber cable, one fiber cable can really hold a lot of bandwidth. You can do terabits on a fiber cable if you have to. For information on that, please refer to my video about why fiber is really like unlimited bandwidth. So BGP is just looking for the quickest AS path from its origin to its destination. But BGP is dumb. All it knows is the AS path. So if the AS path says take this way, it's the shortest, that's what it's going to take. As an internet provider, why I said it's really my job to get it to that core router and then it's going to figure out its way, is I don't have a lot of things I can do to influence which provider it goes out on or which ones it comes into. Because incoming can be a completely different path than outgoing. So on outgoing, I can set rules to say this network prefix only goes out this one path. But incoming, I can kind of manipulate routes by making the network longer over different paths by inserting what they call them prepends and say that it's an extra 10 hops or so, but I can't really force it to come in a certain way. Once it gets to the destination, it's got to do the same thing that we went over in the first part, where it has to take it out of BGP and then find its way to the destination, whether it's a web server, whether it's someone's computer, whether it's some other type of network that it needs to talk to. But it's going to go and be decoupled from BGP and go through its internal routing policy until it ends up at its destination. Each AS path is basically just made up of fiber connections that connect one network for another. Whether it's an undersea transit line, whether it's a local company that's right down the street for you, it's going to go up to this AS number, and then once it's that other router, it's going to see the network as it sees it and choose the next AS path until it finally gets there. Once it arrives at its destination, then it's up to the local routing policy again on that network, on its destination network, to decouple from BGP and then figure out the path of which it switches to get to whether it's a web server or a device or a network that it has to talk to. So a good analogy for this is, say I want to go to Tokyo. When I go there, I'm going to have to take a car to the airport and get onto a plane. Well, that part of me driving to the airport is the local routing topology. Once I get onto the plane, think of that as the internet. You're in the cloud. It's figuring out the quickest way to get over to Tokyo. So when your plane lands in Tokyo, you're going to have to do the same thing. You're going to have to get out of the airport and you're going to have to go through its local routing topology, and you're going to have to take that over to your hotel. And then finally you'll be at your destination. When we do have a problem, there are a few things that we can see what the problems are. One would be traceroute. we can actually use the command traceroute and then destination and see the way that the path travels through the internet. Sometimes there's not a lot you can do about it, but you can see if it's different incoming or outgoing because you can use different trace routes around the internet to see if there are different ways that's coming input versus output, and if there is one hop that's really making it have a problem. The next tool that you have is called ping. Ping and then the name such as google.com. That will tell you the latency or how long it takes from a piece of data to go from your computer through the internet to the destination and then all the way back. Usually these are measured in milliseconds. Nowadays, everything you really should be less than 100 milliseconds or so. Finally, the last thing is a BGP looking glass. This is a little more complex to use, but it'll see if there are problems with BGP. You can see who's announcing which prefixes and which provider they originate from. So if we do have a problem along the way, there's not that much I can do to stop it. And you might have a bad experience going to a site for a day until they can get it fixed. Now there's a lot of cases where that's just unacceptable. You need guaranteed times. What if you're a bank and you got to be able to do credit card transactions with your corporate branch? There are ways to do that. You can get a lease line from a carrier that guarantees the latency, that guarantees the speed and availability. Availability is the amount of time that they guarantee it'll be up a year. Private lines are very expensive. But if you need guarantees as a private business, often it's worth it rather than have downtime. Now, I know there's a lot of moving parts to this, but overall you take them together as a piece and you don't look at it as a system and you can see how the internet works.